Thank you very much. And thank you very much. And after this introduction, I will go directly to the presentation. And yeah, we focus today on you can say basic understanding of refrigeration systems, and to deal with especially with the energy consumption of the main components. You just made the presentation, so I'll just skip this. It's actually what you said, and go directly to the refrigerator. This is a component or a refrigeration system that you probably all know and have at your home. If not only one, you have perhaps only both a cooling equipment and freezing equipment. But basically, it looked like this. And sorry, something is happening here. Go back to this, right? And behind this, you can say behind the outside of this cabinet, you find the refrigeration system, and you find the main components. Actually, at the top of the refrigerator, you find this component, which is called the evaporator. That's where the cooling actually happens, or the air inside the refrigerator is cooled. We find the second main component, which is the condenser. It's placed on the back side of your component and giving actually heat to your kitchen. And the third main component is the compressor, which is normally located in the bottom part of it, giving a little bit of noise. Not much, but a little. So that's basically a refrigeration system that you all know, but probably don't know how it actually works. So I'll try to explain that, and you see on this slide, you will find again all the main components. You find the compressor, you find the condenser, you find an expansion valve, which I didn't tell you about before. And you can find the evaporator, which are actually the main four components which are necessary to keep the refrigeration system working. And all these parts are connected with pipes, and that's actually all we need to get the system running. Of course, we add some refrigerants into the piping, so that we can have a special fluid to go around or circle or transport into the system. And there are some things called superheat and in the evaporator, and there's a thing called subcooling in the condenser, which we'll mention later on. And then perhaps the most important thing about the refrigeration system is that we have a load. We have a load on or heat load on the evaporator here. That's where the cooling is actually happening or taking place. Is that we have the cooling to happen in the evaporator, which means we add some heat to the refrigerant here. We also add some energy to the compressor in order to get the whole system working. It's like a pump. And both of these energy, if you add these together, it is actually rejected here in the condenser. And that's what you find on the back side of your refrigerator. But let's take a look at all these components one by one. And let's start with the evaporator. Here you find you can say this part of the whole system, the circuit with the evaporator where the cooling takes place. And if we take from here, you can see that inside this component called the evaporator, we inject refrigerant as mostly liquid. That's the green color here. And when we add some energy to the liquid here, the refrigerant as a liquid, it actually evaporates, and we get, instead of liquid, we get gas. And at the end of the evaporator, we get what we call the superheat. And you can just compare in your mind or in your head that it's just like a boiling kettle. That also in this, the boiling kettle, you add some energy, and with water, you're adding some energy to the water. It's actually boiling or evaporating, and you get this steam out of it. And that, in principle, it's exactly the same thing that happens in the evaporator. And if we take a look at what real components looks like in real systems, then we find this component here, which is an cooler for air. If we want to have some cold air in, for instance, the cold store, then we put a component like this one in the room. As you can see, there are some big fans which actually get the flow of the air through this core, the evaporator coil, which is inside. That's if we want to cool some air. If we want to have some liquid cooling, then instead of the air evaporator up here, we use, quite typically today, we use a plate heat exchanger, and instead of fans, we use a pump to circulate the liquids and pass through all these plates in here. And inside these pipes, we have the boiling liquid, the boiling evaporation, which gives the cooling effect, and we get some cold liquid or some cold air, which is normally the main purpose, of course. If we take a look at the second main component, which is the compressor, then we find, you can say we have an inlet, we have this, what we call the suction side, and we have the discharge side, and actually we add this energy with an electric motor typically. And it's just like a pump, which I can illustrate by the component that you probably know from the bicycle pump that you use when you get some air inside your what's it called, in your tires. And if you remember, then when you when you operate the pump, you also generate some heat. So it means that it not only increases the pressure from the suction side here to the discharge side here, and makes all the transport of the refrigerant, but it also adds some temperature increase, so it gets hot. Actually, it happens with anything that you try to compress to higher pressure. Then you will also get a higher or increasing temperature. So the gas leaves or enters at low pressure here with a relatively low temperature, and it leaves with a higher pressure and a higher temperature here. And it's all due to the fact that you add some energy through a motor to get the compressor running. If you take your own refrigerator at home, you will find the component looking almost like this, a very small compressor with both compressor and motor built in into a vessel, a small pressure vessel. It contains, you have the electrical part and you have a compressor inside. But if we go to larger system, you will probably find a compressor for industrial application, which looks more like this, with some cylinders in here below each cover here, and there are other equipment out here. We cannot see the motor, but again, we need a motor to be connected here to get this compressor running. Then when we go to the third component, which is the condenser, what happens in the condenser here is that we actually get the hot gas, you can say here from the compressor, which I just showed you about. We get the hot gas, refrigerant as a gas, entering the condenser here, and it's still as a gas. But when we get some cooling here, which actually means we remove some heat by using water or air to get some cooling on this very hot gas, then it turns into liquid again. And then you can see the more energy we reject or remove from the refrigerant here, the more liquid we get at a higher temperature and a higher pressure level. And if we continue to cool this this refrigerant by air or water, then in the end we get what we call subcooling, that the temperature of the liquid is a little bit below boiling point. But in principle, the energy that we extract here is the amount of energy added to the evaporator plus the energy added to the compressor, and then perhaps 10 to 15% in losses. But the process of the condensers could be a little bit difficult to understand. So what I tried here is to give you an illustration of what happens if the moisture in the air meets a very cold surface. Then it turns into droplets, as you can see on this one here. Or as in another illustration, again, if you meet something very cold, then the gas form enters to liquid form or changes to liquid form, and we get the liquid here. And in principle, that's exactly what happens in the condenser. Again, if we look into real life and see the components, what they look like, then if we have an air cool, or we want to cool the refrigerant in the condenser with air, then we typically have a air-cooled condenser, which has, again, fans to operate here, in this case 3. And the ambient air gets from below typically and is rejected from the top, giving the cooling of the refrigerant, and the refrigerant enters and leaves this connectors here, the common lines, and gets back into the refrigeration system. That is if it's air. If we use liquids to make this cooling, then the component could look like this. It looks, or we call it a shell and tube type of heat exchanger, and typically the refrigerant gets into the top here and leaves at the bottom here, and we get the water, the liquid that we use for cooling is actually entering and leaving here at the end of with the end cover here. The last component, main component that we need in a refrigeration system is the expansion valve. In this symbol here just measures or shows that there's a flow direction here, and we have, in principle, at the inlet we have liquid coming from the condenser up here in the system where we were before, made by the condenser. And at the outlet of the expansion valve, we find both liquid and gas, actually, not only gas, but a mixture of liquid and gas, which is actually delivered to the evaporator. And again, to show you something you can compare with, it's just a simple valve. It's not a valve like this one. A real valve looks like this one. This is what we call a thermostatic expansion valve. And this bulb here typically measures the temperature. It's connected here at the outlet of the evaporator on the pipe, measuring the temperature of the gas leaving. And that signal, you can say, from the temperature here is entered into a membrane in here, diaphragm. And you get the liquid coming in from the bottom here and leaving into the plant through this section here. There's an orifice inside which looks like this. The main function of the expansion valve is simply to deliver liquid for the evaporator. Always deliver liquid enough which matches the load of the evaporator here. So the main function is simply to deliver liquid, not too much, not too little, to cover the need for the evaporator for the cooling. So here on this slide again we see the system again. We see all the components. I've added all these illustrations to show you what happens in the different components. But if we continue just to see what happens, then of course we should add some refrigerant to the system and put it into the piping. And in this case I've just mentioned or chosen a refrigerant used typically for normal cooling systems called R134A. And if we use that system or that refrigerant into the system and try to put it into a normal or some cooling purpose, then then we can see now here on this side here that by operating the compressor here, it will produce a suction pressure in here, and the suction pressure here can say also is inside the evaporator here, and which actually gets the liquid in here, the refrigerant inside the evaporator here, to evaporate. And instead of water, as we know, evaporates at 100 degrees, then the refrigerant evaporates or boils at perhaps -5, as in this example here. So, and if we want to, for instance, cool down some air, then the inlet temperature of the evaporator could be perhaps +5, meaning there's a differential of 10 degrees from -5 to +5. And this, you can say, small differential temperature actually is enough to get this the refrigerant boiling inside the evaporator. And what happens is, of course, that the air gets cold, and perhaps it leaves at a temperature of +5, meaning that we have cooled the air about 3 degrees. And the refrigerant inside here, inside the evaporator, the gas, when it changes from liquid to gas, then it has to be heated up a little bit more so that we are sure that it's gas that enters the compressor. If we get liquid from the evaporator to the compressor, we damage the compressor. We call it liquid hammer, and it's not very healthy for the compressor. If we continue you can say to follow the circuit here, then as I told you, the compressor will actually produce the suction pressure. And in this case, using this refrigerant, we end up with 1.4 bar overpressure or gauge pressure. It should always be above atmospheric pressure in the system, because if it's below, then if there's a small leakage in the piping system, then we introduce air and moisture into the system, and we don't need that. We try to avoid it. So giving it a superheat from the boiling temperature of -5 in here, then perhaps the gas temperature entering the compressor is about 3 degrees. When the compressor is running, as I told you in the beginning, then the temperature will increase and also the pressure. So in this case, in this illustration, you can see that the pressure is increased up to about 8 bar, still gauge pressure. And the temperature is also increased to 75 degrees. It's quite hot, actually. You can sort of burn your fingers if you connect it to the pipe here after the compressor normally, even in your domestic refrigerator. So you can see both pressure and temperature increases. Then we should get back to the liquid again. And in this case, you can say we operate, as an example, with a condensing temperature of +35. And that actually means that inside here, if I put a temperature sensor inside this condenser in here, then you will measure the temperature of 35 degrees all over the system where you both have liquid and gas. So the temperature of, you can say, the transformation from gas to liquid, the temperature of the mixture in here will always be +35, as in this example. And to do the cooling, we need something colder, so I enter perhaps ambient temperature of +20. Gives a temperature differential about 15, perhaps a little bit more than we would like. And of course, the air enters with a higher temperature because it's cooling down this one, and it gets the heat from the refrigerant, and perhaps it leaves at +24 degrees. Then we have produced the subcooling, or the liquid, and if we continue to cool it a little bit here, or in the piping here, or perhaps in the receiver, then we get a temperature a little bit below the condensing temperature here, 35, in this case 32 degrees C. And the reason why we want to have this subcooling here is that we will be very sure that we don't have any gas, we call it flash gas, means evaporating refrigerant in the pipe in front of this in the orifice in the expansion valve. Because if we have some bubbles in here, then the orifice will not be able to cope with it, and we get less refrigerant to the evaporator down here. So we have a malfunction actually if we don't have this subcooling of the liquid in front of the expansion valve. So basically that's what happens in a refrigerant cycle, actually in every refrigerant cycle, what we call a one-stage cycle, the compressor that makes the pressure differential. This is just a slide showing you a little bit what kind of refrigerants we add to the system. There are quite a lot of them, and I haven't put it on the slide, but today we are a little bit concerned about, or more concerned about, the environment as before. So we try to use what we call natural refrigerants, which is not harmful to the ozone layer or the what we call GWP, the global warming. So what we find here on this side here is actually what we call natural refrigerants, and ammonia and carbon dioxide and hydrocarbons are refrigerants coming in this side, which are actually the refrigerants that we want to use in a long term. We're still using a lot of other refrigerants, but you can say the goal is for the future to go to natural refrigerants, which actually exists in the nature already. Coming back to the refrigerator, I call here a small refrigeration system. Just another illustration of what happens inside is that we have again the condenser, or which is have the evaporator up here. We enter some liquid inside here. It evaporates in a coil. We have what we call a suction accumulator at the top, which separates liquid and gas at the top, so that it's only gas which enters here back to the compressor. It gets compressed, temperature increases, pressure increases, and we discharge the gas here to the condenser, and it gets to the backside of the refrigerator through this coil. In this case, it's sort of split up in two. That's not normal, but it's split up into two. And the refrigerant is getting back into liquid state, and we even put it into a small vessel, or a dryer we call it, and instead of an expansion valve, we use a capillary tube here to inject the liquid back to the evaporator up here. So we find exactly the same, not some other kind of a components, but exactly the same system. But we have talked about small systems now. Of course, we have some very large cooling systems as well, and I just mentioned one system built in Germany for storage, I think, of different kinds. In this case, as you can see here, we use ammonia or CO2 as refrigerants, and we have a very large piston types of compressors. And we operate with, in this case, about 600 kilowatts with cooling at minus, what the evaporator is evaporating at minus 11 and condensing here at plus 40. So very large compressors. We use condensers. And again, you can see the capacity is larger than what we found on the capacity of the compressors. So we use an ammonia condenser and a CO2 condenser, carbon dioxide. And we use evaporators. Capacity here is about 350 kilowatts, or the air-cooled, or the evaporators for air cooling is approximately 25, and that's 5 of those mounted at the ceiling. You can see one of them up here actually. So in principle, the same system for both small and large systems. But you can say the same kind of system can be used both for cooling and heating. So what we find here in the illustration here to the right is that we have exactly the same systems in 3 versions here. And if you take the condenser side, here, and it is the condenser, the heat from the condenser that you actually want to produce with the system, then we call the heat pump. If it's the cooling on the low pressure side and here on the evaporator side, then we call it just a refrigeration system. And what is of course the best is that you both have a demand for cooling and heating as well, and you actually have the same demand and the same time. Then you can call it a heat recovery or an energy system. So that's of course the very best if you can do that, and it's done more and more in real life. So to come back to the introduction, which we had, then you can see that in Denmark, if we calculate how much energy, electrical energy, how the amount of energy, electrical energy used for cooling, it's actually about 11-12%. It's quite a lot, and perhaps half of it is for domestic refrigerators and freezers, and the rest for, you can say, commercial or industrial applications. So we have a lot of very small domestic refrigerators in a very large number. And then we have this industrial or commercial systems for cooling and freezing in you can say limited numbers, but still enough to perhaps cover half of the electrical power used up here. This slide here, the next slide, shows you an example of a large cold store facility in Denmark. And what we can see here is that instead of having just one evaporator, we have several evaporators here. In principle, it could be one room or two room, but in this case, you can see a number of evaporators here, and each of them are having a fan to circulate the air and passing the evaporator so that we get the air distributed into the cold storage area and cool down. We also have compressors here, two of them in this case, and we also have some pumps. The main energy consuming components inside these larger systems is the compressors, which in this case we have two, and it's a large number of fans in this case, large energy consumption, but not as much as the compressors. And then we have a number of pumps. In this case, the pump is circulating liquid, refrigerant liquid here and here. In this case, it's a water pump, and also at the condenser side, it's a water pump. So you can see the energy consuming components is here is typically compressors, fans, and pumps. And what we try to reduce power consumption, to decrease power consumption, is actually to minimize the energy to the compressors, electrical energy to compressors, to the fans, and to the pumps, and to minimize this. And to do that, we look at, you can say, what can we do about these energy consumptions? Well, we can select some efficient inverters if we run with speed control. We can select the motors with high efficiency at full load and part load. We can use or select compressors with high efficiency, again, both at full load and part load. Especially, you have to think about both full load and part load. It's about pressure differential from suction to discharge, of course. The more discharge, or the larger pressure differential from inlet to outlet, the larger amount of energy you have to put in. And then, of course, the operating time for each component is also calculated to get the energy consumption. And in principle, it's exactly the same. You can say story for fans and pumps. Again, inverters, motors, and in this case, pumps or fans is the same. And the pressure differential is the same, and the operating time is the same. So it's all these components that we, or elements that we're working with. This slide actually shows some data, quite a lot of data, I know, perhaps a little bit confusing, but I've chosen a small compressor just to see what happens with the energy consumption of this very small German compressor from Bock. And I've chosen here number 1 here is, you can say, the basic reference situation where I operate at -10 at the suction side and the evaporator side. I have a condensing temperature of 40. I have a suction gas at the end of the compressor at 10, meaning we have a subcooling of 0, and it means we have superheat of 10. That's the difference between this 10 and -10. In this case, the compressor has a certain capacity measured in kilowatts, and it has a power consumption here. And if you calculate the energy efficiency ratio, which is you can say the ratio between these, you get a factor of 3.7. But what happens if you actually try to increase or decrease the suction pressure? Then we get to this number 2, which means I decrease the pressure and the evaporating temperature here 5 degrees from -10 to -15. And as a consequence, I get a lower capacity, I get a lower power consumption, but the efficiency goes down. And the ratio here between this figure and this figure here is 0.16. You lost 16% in efficiency. And if you do the same thing with the condenser, meaning you increase the condenser from 40 to 45 with 5 degrees, you lose capacity, you increase power consumption, and you lose efficiency. So the consequence of all this means that the energy efficiency ratio, as you saw, is decreasing when you decrease evaporating temperature or increase discharge pressure, because in that case, of course, the pressure differential gets higher and the power consumption gets bigger and the efficiency gets limited. If you try to use or change superheater, it's not significant at all. It's only very, as you can see on the figures here, it's very low. So no problem there. But the main conclusion, and that's very important, is that you can say for each degree here you change, either the temperature of the evaporator side or at the condenser side, you change the power consumption or the efficiency from 2 to 3%. And as you can imagine, that is very easy. Or if it's just changing 1 degree, you add change the energy consumption by 2 to 3%. So it's very, very important to have as low condensing temperature as possible and as high evaporating temperature as possible. And still talking about energy possibilities to decrease energy, then sometimes we use pressure regulating ratios into the system. In this case, we can add a valve in here. We can also add a valve here at the top, which we call a capacity regulator, or we can add a condensing pressure regulator. And what I just want to say is that any kind of regulating valves increase energy consumption, because either the suction pressure here gets lower, meaning again 2 to 3% per degree, or the condensing temperature here gets higher, the pressure gets higher in case of these valves. So try to avoid it if you can. And coming back to actually the title, which was about intelligent control, then this is also a little bit complicated, this figure, but let's try to just explain again that what we really want is some temperatures in the system to operate as we want. So we use what we call primary set points. But in reality, to get these temperatures which we want in the system, we have to use some secondary set point, meaning we have to adjust the evaporating temperature or set the evaporating temperature, the condensing temperature of the system, or some other temperatures in case we use prime or indirect systems. Put these into some regulators with PID, put it into the operation of the compressors, fans, and pumps in the cooling system here, measure getting back, and what we like to do is to have this box of intelligent control, which actually takes care of, you can say, you can say, the total energy consumption of the whole system. So, and that's what we normally do. We have these set points, but what we would like to do with this is actually shown on the next slide here, that instead of using a fixed evaporating temperature, then we'd like to have, you can say, a floating evaporating temperature that this intelligent control actually optimizes the actual suction pressure, meaning the evaporating temperature. Because if we take a look at energy here and temperatures, then we find that the energy consumption of fans and pumps goes up, and the temperature or the curve of the compressor goes down. So if you add these two energies, the power consumptions of the compressor and the fans and pumps, then you'll find a minimum of energy consumption on the low pressure side, which is a combination of the compressor and the fans and pumps. And that's where we like to have this set point to get floating and always adjust to the minimum energy consumption of the fans and pumps together with the compressors. And exactly the same goes for the condenser side. Instead of having fixed condensing temperatures or set points for condensing temperatures into the system, again, we use compressors at the discharge side. We have a curve for the compressor here. And we have a curve for the fans and pumps on the condenser side and the high pressure side of the system. And again, there will be a minimum of these two energy consumptions for compressors and fans. And the system should be actually operating at this minimum here all the time. And that's what we try to put some energy control into, sort of getting this floating set points all the time. So basically that's what we call intelligent control. So in principle, that's all, folks. That's what I had to say, and you can find my contact information here on the last slide. So that was it.